This program was brought to you by Koller Institute of Venture at Tel Aviv University.
This is a quote from J.J. Thomson, who's measured the ratio of the charge to mass of the electron, considered to be the discoverer of the electron. And he said, if government and industrial laboratories had been operating in the Stone Age, we should have wonderful stone axes, but no one would have discovered metals. So it's not only about people calling on the phone because they have an idea of an application. And this is what I'm going to talk about. I'm going to talk about enabling technologies. I don't want to do the mumbo-jumbo part of defining exactly what is enabling technology, but I want to give you an example that sometimes we have to do a quantum leap, קפיצת הדרך if you want. And we need to import something from the realm of basic science and make it into a viable engineering capability. And this is what I'm going to talk about today. And in order to make it easier for you to follow the pattern of my talk, I want to tell you an anecdote about Oliver Wendell Holmes, Chief Justice of the United States of America, considered by many to be America's greatest juror, perhaps. You would probably prefer Brandeis if I listened to your talk, right? So he was notorious for being absent-minded, and he was going home at the end of the week to Boston. He sat in his compartment on the train. Conductor came in, and he said, asked to see the ticket. So Chief Justice Holmes was looking in his pockets, couldn't find the ticket. He stood up, looked under the seat, couldn't find the ticket. Conductor, of course, recognized the passenger, and he said, Mr. Chief Justice, I'm sure when you get home to Boston, your housekeeper will find the ticket and she can send it to the railway company. So Holmes looked at him and he said, young man, you don't understand the problem. The problem is not where the ticket is, the problem is where am I going to? Okay, so I'm going to do here a combination of past and future case history, and let me apologize first, because my late father used to say that I don't brag about myself, but I admit I'm good. So it's going to be about things that I did with my students in my research group at the Hebrew University, previously at Caltech, and that's it. So I mean, I'm not going to talk about centers and stuff and big organizations. It's a small research laboratory in a university, and that's the emphasis, in a university. Okay. So in our example today, the destination is going to be solving the data traffic overload in data centers problem. I'll explain exactly what is the problem and what are data centers. I'm going to talk about the ticket. In other words, what is the solution? And this is a concept that I came up with. It's called dynamical optical circuit switching. And I'm going to talk mainly about the train, which is the technology for implementing the solution. And it's based on a concept called electro holography. And I'm going to talk about all these things, trying not to be technical. It's not simple for me. Okay, but I want to make a point here. They are in totally different domain. And one of the things that I want to leave with you here is that one of the major problems of making an invention becoming an innovation is to bring together these different domains. And I'll elaborate later. Okay, so the first sentence in this video is, tell me, Vin, what exactly is electroholography? So first, who are these people? This is an old video. It's low quality, maybe 15 years old. The person on the left is Alexander Haig, former Secretary of State 4-star general, commander of NATO. And the person on the right is less known to the general public. He's actually the inventor of the internet, Vinton Cerf. Today he's, at the time, by the way, talking about universities, he was a professor at the University of Southern California in Los Angeles, and now he's vice president of Google for global development, something like this.
Now then, just what exactly is electro-holography?
Well, let's see. Imagine for a moment you have a laser beam and you split it into two different parts, and then they are put back together again. Depending on the delays, you get interference patterns. You can take those patterns and you can actually use them to interact with the inside of a lithium niobate crystal. Inside of that crystal, you have what looks like an invisible interference pattern that you can't see until you turn up some of the voltage on that crystal, and then suddenly the interference pattern becomes more visible, and light that's coming into the crystal can interact with it and can be steered. And so, Tim, I hope I haven't done too much damage to the basic concepts. It's a beautiful piece of physics.
Thank you.
But you're turning this into a product.
Okay, so what happened since then? By the way, imagine me, I actually invented the word electroholography for some research grant I was writing. I wanted to catch the imagination, whoever decides. When I saw this film, a video for the first time, and he didn't ask me anything about it, he just read the papers. And he did it pretty well. I'm sure he couldn't follow it, but he was wrong. In one point, it's not lithium niobate crystal. We'll talk about it later. Okay. So I'll explain what is electroholography later on. But let's start with the problem. Data centers. What are data centers? They are facilities that are being used for housing a variety of cloud computing services. Actually, the main large-scale applications today are done in data centers: distributed computing, distributed storage, big data analysis, virtual machine migration, video on demand, et cetera, online games. And they are huge facilities. You see this building, it's an example. It houses rows after rows of cabinets, side by side. Each cabinet has racks. Each rack has servers housed, installed in it, and there is top-of-the-rack switches that are used to connect them. There are, in the large data centers today, huge numbers, approaching 1 million servers, and servers are pretty sophisticated computer systems in each data center. Think about it. Give you more numbers. Such facilities, the large data centers, are about square kilometers in area. They, as I said, about 1 million servers. The data centers in the United States are consuming 2% of the electricity produced in the United States. It's an unbelievable number. But what is more interesting is the amount of data that is being moved there back and forth. The forecast, this is a Cisco forecast. In 2017, the data into the data center, outside the data center, and within the data center is going to go up to 7 times 10 to the 21 bytes per year. And you see how it's divided, and this is the source of the problem. It's divided by, you see 76% of this huge, humongous amount of data stays within the data center, going back and forth. We call it east-west traffic, as opposed to south-north traffic, which is out of the data centers into the data center. So most of it happens inside the data centers themselves. Okay. So how this humongous data traffic is handled, and it's done in a schematic way in this 3 layers architecture. You see the servers here, and they are connected. Each group of servers is connected to a switch that is called aggregation switch. The aggregation switches are connected to the next layer of core switches. There are very few of the core switches, and they are very sophisticated. And then it's connected to the other switches, and then to the next group of servers. You see there's almost no intra-traffic here in this architecture. Here, And here, there is some, of course, here. This doesn't work. It's clear that it's not going to be a solution. The amount of data that is moving back and forth in the data center grows exponentially per year, and it's not going to work because it doesn't scale. So it's becoming a critical problem of computer engineering. But there is light, literally speaking, as you will see, at the end of the tunnel, and this is what we call mice and elephants. 99% of the messages that are being sent back and forth are called mice because they're very small. There are very few bytes there, okay? Less than 100 megabytes, okay? 10% are what we call elephants, the larger messages. But the point is that these 10% carries 99 flows are mice, 1% are elephants. This 1% of elephants carries 90% of the data. Interestingly enough, when I started with this, I didn't see this slide. And but intuitively, I say people are sending video on demand, large movies, large backups, especially after 9/11, backups became a big issue in the internet, et cetera, et cetera. So large packages, large messages is becoming something very abundant, and this architecture, 3-layer, that is going packet by packet, small packets, packet by packet, is not efficient for this kind of data management. So I thought about the solution. At some point, the solution became too complicated for me, so I enlisted a colleague from the School of Computer Science at the university, Professor David Chai, and he showed me this thing. So I found out that what I thought intuitively was actually correct, and it's becoming more so as time goes on. So what is the solution, the ticket? I call it dynamic optical circuit switching. I'll explain it in a very schematic way. So I add an auxiliary network to this 3-layer network that works in a different way. And this is a network that allows me to connect pairs of points, pairs of servers, or actually top-of-the-rack switches, but schematically it's the same thing, directly to one another. So if A wants to send a big chunk of data to B, it's connected to it physically. Okay, much like the circuit switching that we did in telephone electromechanical exchanges in the 50s and 60s and 40s before that. Okay, so here is one such connection. Okay, and here's another one. But the point is that I cannot do it with too many connections. I cannot build too many physical connections that exist at the same time and connect all the possible points that I need to be connected whenever. So the trick here is that this connection can evaporate. Okay, if you saw, okay, you see the black now, the purple, now the black disappeared, so I can use the resources for the black to do another connection. And now I'm coming to the 3rd layer and how it is done, okay? So what is the train that these tickets allow me to board? Okay, so my students are very good, and this slide was made by my PhD student, Sagi. Okay, these are the mice. The mice will now go in the regular 3-layer conventional network. The elephant will use the DOCS network, which is marked here as this loop, okay? And they will go like this, okay? And I can send many elephants at the same time, but not all the data in the network, but just maybe 10,000 elephants in a big data center. And so this was the point where we decided to check it out by simulation. Okay, we don't do any we haven't done any physics yet. It's all conceptual. But we asked ourselves, what happens if we equip a data center with this DOCS auxiliary network? And I'm not going to go over all this, but if you look here, for example, it's a which one I wanted to show you? Let me look here a little bit better. Okay, if you look here, you can see here we have the overall data that is at a single point in time in the data center. Here we have the delay that is encountered by data that is sent from one point to another. And you see that the delay here is rising, and it's very high. But once I started building in DOCS circuits, and you see here what the colors signify. Black is zero circuits, in other words, the classical architecture of the data center. Red is 1, etc., and brown is 50. And you see that if I give this data center 40 circuits, I take down the delay by 3 orders of magnitude. So it becomes much more efficient. I'm not going to analyze this. I have many other slides to prove it, but you'll have to believe me, lunch is approaching. So how does it work? Exactly, here is the auxiliary network. And let's say that I want to connect these 2 points. So what I do is I use a concept from optical communication, fiber communication, which is called wavelength routing. It's not being used today. It's not, the technology is not right for it, but the concept exists for quite some time now. And what do? I create a loop with a fiber bundle, many fibers, one next to the other, and the points that I want to connect reside along this loop. And I assign a fiber and a color to pair of points that want to connect to each other. So one of them will transmit on this fiber at this color. The other one will listen to this color on this fiber. So when I do this, they are physically connected, like so. Okay, and they can continue send information from one to the other as long as they are assigned the fiber and the color. Okay, I can do several at the same time on the same fiber because the colors do not mix. Okay, so here is what happens when I do 2 on the intermediate fiber there, and I can go on with this forever. I learned to do the animation for preparing this slide, so I'm in love with it. Okay, so let's go on. Now we come to the train. In other words, what is the physics? How can we build this thing? And we need 2 families of devices. One of them is what we call wavelength selective switches. In other words, devices that allow me to split one color out of a group of colors. The other one we call wavelength tunability. And wavelength tunability is that we can select a color from a light source to be used in an optical transmitter. Okay, so we need these 2 groups of devices, and the state of the art of photonics engineering today cannot implement these functions that can do these functions fast. Okay, if I want to do it, I have to build a system with different devices. And building a system with different devices means that it's cumbersome, it's expensive, and it's slow. Okay? Furthermore, the roadmap for the implementation of this devices is not anticipated at the present time. Okay, so it's finally time to board the train, and boarding the train means bringing the concept to build these devices, electro holography that I mentioned before. So what it is, now you can see what it is. It's an old slide. just to give you an idea, the guy who prepared this slide was my student at the time, Guy Bartal. He's now professor at the Technion, so you can imagine how much time elapsed since it was prepared, but still, it's a nice slide. So here is the device. The device is a crystal. We'll talk about it some later, in which we embed a hologram. And the way it works is like so. The hologram is transparent. So if I come with a bundle of light beams at different colors, it goes through, and it is transparent as if it doesn't exist. But once I apply an electric field on this crystal, one color comes out. Okay? So it sort of, the hologram is dormant, and I activate it or wakes it up when I apply the electric field. This is electroholography. But it's a concept, and in my world, this is optics. I now have to go to physics to find out how I can actually build it in the lab and later on in the industry, okay? So question is, in principle, can electroholography be the basis for a viable technology for implementing donks? The answer is yes. You'll have to take my word for it, but give you one example that we built in the lab a few years ago. Here is a tunable laser, electroholographic tunable laser. We built it from parts on the table just to see that it works, and I get wavelength tunability of 50 nanometers, probably the world leader in terms of the width of the tunability today. Okay. But what does it take to make it into a viable enabling engineering? So let's see what the basic research in the academia, in the realm of the academia gives us. This is the most frustrating slide for me in the whole presentation because I'm a born tinkerer. Nathan will testify to that. And in this slides are encompassed maybe around 80 papers in different scientific journals, starting from Nature Photonics, Optics Express, Optical Letters, Physical Review, et cetera, and I can't talk to any of them. And this is the world where I live, and not so much in the engineering world. Anyhow, so the basic research in the academia gives us this in terms of the train that we want to board, the functionality, which is electroholography, and actually more than electroholography, the device physics for its implementation, something that I call paraelectric electro-optics. It's a new kind of device physics that is not being used today, based on principles in physics that are not being used for engineering uses today, and the material system for its implementation. It's a special crystal that I invented. It's called the KLTN crystal. At the present time, it's being used by my wife in one of her pairs of earrings. It's a beautiful crystal. Okay. So again, functionality, electroholography, wavelength selective switching and wavelength tunability, device physics for its implementation. Let me check you out. And the material system, okay? And this is what I can get out of the academia. So it's a proof of concept in principle. Or actually, I have experimental proof of concept, but it's not engineering, okay? So in order to move forward, this is the conclusion of the academic phase. So in order to move forward, I need a little more than that to make people interested. And proof of concept of the functionality, I showed you one example. The device physics, it includes a full evaluation of the performance envelope of the devices that are going to be based on this device physics. And I mentioned here too, one of them is the switching speed that we reached 0.9 nanoseconds. It's 3 orders of magnitude than optical switches today, and they are not wavelength selective. And this one is wavelength selective. And also, it gives us fast electro-optic operation through the entire visible and near IR spectral range without developing optical damage. This will be very important in 2 minutes. For those of you who are not active optical communication engineers, I would just say that optical communication works in the infrared, at around 1.3, 1.5 microns wavelength. Visible is 0.4 to 0.7. So why is it important? In a minute. Okay? And the material system. We need not only to have the crystal, grow it in the lab for research purposes, but we need to have a way to grow it in sufficient quantities with sufficient yield to support all the development, a process that will follow if it follows. And here starts the chasm, because here we start to do things differently, not the way they're done in universities. What we did so far, and here I think I'm not agreeing with Yesha, this can be done only in universities. Until now. But now we have to change our modus operandi, and so that means that we have to bring in new players, and people are talking about this chasm from here to eternity. Where is the good point to bring financial funding? It's not ready yet for financial funding, and yet the university has concluded its capabilities here. So what do we do? So the chasm, or the Death Valley, sometimes it is being called, I don't like this expression, but nevertheless. So what do we do? So does it make sense to venture funds to invest in electroholography at this stage? And I'm claiming the following: yes, provided that we understand that data centers are early majority market. In other words, it has certain rules, meaning that the new technology is not going to go in there. Something new does not go into the early majority market. They don't take the risk. They require different things. I refer you to the book by Jeffrey Moore called Crossing the Chasm, surprisingly enough. He will explain what is the difference. In order to bring a new technology into the market, we need to have what we call early adopters. So what are the early adopters here? We are aiming at a problem which is a huge problem, but it's a early majority problem, not early adopters problem. It's different people with different constraints, different rules of the game. And here comes the fact that these devices work in the visible, because here we can find many early adopters. Tunable laser in the visible, for example, that are done in integrated, I may go over a little bit, that are done in integrated devices, et cetera, et cetera. So, but the understanding of what is written on this slide is not understood in universities, because the people in the university who work on device physics do not understand about these things. To a large extent, engineers do not understand about these things either. So we need to find people who understand both the physics, engineering, and the business to go on, and this is my point in this talk. As I said, the chasm can end here. And here is my 2 bits of wisdom how to do it. To understand that this is not a relay race. It's not the university stops here and the venture funding starts here. There is an intermediate phase where they have to work together and to make this technology happen, because it requires the capabilities of both working together for a while. And this is something that sounds trivial after my talk maybe, but it's not understood at large. So we have to identify the early adopters and produce the roadmap to its implementation. From preparation of the business plan to the foundation of the implementation environment, I don't use the word startup because it's not necessarily startup. It can be a strategic partner. It can be something that happens in government research laboratories sometimes. And we have to identify the early majority because we have to nurture the solution of the early majority. Fortunately for us, we have computers. We could do it in simulation. And the information is important because we pump it back to the physics level in order to optimize the performance, in order to create the optimal future technology to address the problem of the early majority. I want to go to entirely, at the end of my talk, entirely different example taken from the history of digital microelectronics. First of all, these are two patents. I don't have time to go into details, but if you look into the details, they are very similar. And yet, they are 6 years apart. One of them is English, the other American. I mean, the inventors. Nothing happened when this was invented. Johnson is English. No one knows his name today. Okay? Kilby is one of the people who made integrated electronics happen. And what happened in between? Talking about early majority and early adopters. You know who funded the development of integrated electronics? The space race. Why? Because the Americans were not clever to build strong rockets like the Russians. So they could not put in orbit satellites that were very big. So they wanted to optimize the performance of the electronics, in other words, to build smaller electronic circuits, lighter, that can do more functions. So they funded the development of integrated electronics. Very few people know this. All other things happened in parallel. I don't want to go into the details of that. So my point of early majority, early adopter is made here. Two final comments that you saw. Let's go to the second one. This is if there are venture capital funds people here, by Arthur Goldberg, also Supreme Court Justice. If Columbus had an advisory committee, he would have probably still be at the dock. And with that, I prepared my own. Thank you very much.
This program was brought to you by Koller Institute of Venture at Tel Aviv University.